Okay, I think I can get started. How's everyone doing?
Good.
You guys still hanging there? Okay. Here is what I'm going to do. I'm trying to testing out. Okay, you will see my two names on the screen. I think. Well, I'm using another account to log in and then trying to share my whiteboard. And then I'm trying to record it. I don't know how how it will go. Let's try that. It's a whole new experience to me. So I see it's quite difficult because I need to write out on board. So let's see if it's workable or not. Okay, we have 21 participants right now, and we are going to have 40 tomorrow. I don't know if the internet is in there, but anything you will see anything different, or you cannot hear my voice, just let me know. Okay. So, okay, let's go through homework. The first one is number 4. I think I'm looking for trouble right here actually, because it's not easy question to solve. Let me see if I can do as well as I can. Okay. So first question is number 4. Number 4. Wow, it's 2 things. Could I change that? I think so. Yeah, well, it's fine. Okay. Could you guys see whiteboard?
Yeah.
Okay, sounds good. So right now we do have x1. I do have x1, then to xn, follow normal theta. Of course, theta got to be positive because it's invariance. So in A, we are looking for CILB. Well, it's been a long time ago, right? Since last time we talked about it. So let me remind you what CILB is. So I can have that taken out. Okay. So CILB by definition is what? I have a numerator, denominator. In the numerator is d tau theta, d theta, then taking square. In the denominator is expectation. Original one would be it. I have a u function, the score function, taking square. Right, then take expectation. Okay. And then the score function by definition is partial theta, then log of the joint PDF. Okay, and remember we talk about we have different forms in the denominator. We can either say using score function as a joint PDF, or we can actually write down it's what? I can also write down right here it's n times score function of single observation. It's not actually correct right here. Let me pull that out. Well, I don't know what it's not yet. Okay, so in the denominator, I can either write e as a u function theta, then taking square, or I can actually write down it's what? N times n is outside. And expectation, then inside would be only single one, single PDF. Single PDF would be partial theta, then log. Only single one. Okay? So this guy, join PDF. This guy, only single PDF. Okay? And then there's only one n right here. Okay? So I think this is ID case. So I can use a single one. So right here it's, if you're writing down the single PDF, right here, by definition, it's 1 over square root of 2 pi. Inside is sigma square. For distribution, sigma square is theta. And then expectation, then minus 2 theta. Then x1 minus theta is a mean they're taking square, right here, taking square. Okay, so then you're deriving your log PDF. Log PDF right here. I think right here it's I have minus half log 2 pi theta, first one, then minus 2 theta, x1 minus theta, then taking square. Okay? Then by definition, you derive score function, you partial theta, f of x1 theta equals, then minus half. This guy right here is 2 pi theta and 1, then times 2 pi as a chain rule. Okay? And then right here is kind of tedious if I want to do partial. Okay? But it would be easier to do this if it's a partial theta, then 2 theta, x1 minus theta, then taking square. It would be easier actually if you really expand it. So xi squared minus 2xi, then plus theta squared. I find would be easier. Okay, so then this guy equals, let me see, 2x1 squared inverse theta minus 2, right? This guy is theta inverse. And then minus x1, and then cancel out. Again, this guy is theta inverse, because same thing. And then the last one would be half and then theta. Then you partial that theta disappear. Okay, I think it should be correct. Let me see if I do that correctly. I think so. Okay. Then of course you can do it by definition, trying to take expectation, right? Take expectation. Right here. Okay. That means you take expectation on the whole thing right here. You could do that. Okay, but again, it's you need taking square by score function. Okay, by definition, right here, you take a score taking square, then take expectation. But if you remember, I said it. If you do that, you will find you need to take expectation on something taking false moment, which you don't really want to do. Okay, so then we talk about it. Let me take out some of that. We also talk about it. We can also do second derivative on the denominator, which is I could actually deriving its expectation minus taking second derivative on log single PDF. But again, you put n before that to get eventually denominator of CRLB. So that's what I'm going to do because it's easier to do so. Let me see if I make it correctly. So you guys, if I do something wrong, let me know, okay? So then let's do second derivative. Taking everything out right here. Oops. Okay, so okay, sorry about that. So this guy would be partial half x1 squared minus 1 theta minus 2 minus x1 minus 1 theta minus 2, then plus half. Okay, So doing second derivative again, log f of x1 given theta equals to what then? Okay. Oh, there's one thing right here, right? So this guy need to do second derivative as well. Cancel out, cancel out. So taking second derivative, let me see, minus half, then minus 1, then theta minus 2. Okay, then minus half x1 squared, then minus 2 theta minus 3, I think. Okay, then plus, let me see, then plus x1 minus 2 theta minus 3. Okay, I don't really feel good about this. Let me check my solution key to see if I get that correctly. Oh, I think so. Okay, so I don't have much space, so I'm going to taking out by any means. Is you guys can double check it if I direct correctly. So let me take out this. Okay, let me take out this. So I think eventually partial, okay, partial theta square, then log f of x1, a second derivative is going to become 1 minus theta square, then xi square, then theta. This is x1, then minus half it. Okay, so that means we can eventually deriving CIOB, but we still need to do, let me see. Okay, we still need to do expectation on minus partial theta square, then log f of x1 given theta equals to. Okay, so that means you take expectation on this. Of course, don't forget about this minus side right here, minus side right here. So that means eventually it's you need to expectation on 1 over theta square, then theta x1 square minus half. Okay, so that means you just follow what expectation is. For example, right here you do have this guy is 1 over theta cubical, then expectation, then x1 square, then minus half 1 over theta squared. Okay, so okay, there's no much of rooms. I will need to take things out. Take things out right here. Okay, so then that means you need deriving what expectation of x1 squared is. Okay, if you look at something square expectation, you imagine that you should using its variance, then plus expectation of x1, then taking square. Okay, so that means you can follow that variance x1 theta, then expectation x1 theta as well, then plus theta square. Okay, so that means the denominator of Kramer lower bound is going to be n times expectation. Let me just jump a little bit. So, okay, denominator right here, n times what? in terms, you do have whole thing right here. It's 1 over theta cubical, then theta plus theta square, then minus 1.5, then 1 over theta cubical h. Okay, let me make sure everything is correct. And times minus yeah, I think so. Good. So I'm going to skip the detail and I told you the right answer directly. Eventually, this guy right here is going to become 2 theta square, 2 theta plus 1, then times n. Okay, good. So that means eventually the whole thing of the CILB maybe I can write it here directly. It's so this guy equals, okay, denominator, numerator also theta. So d theta, then taking square, nothing but 1 square. Okay, then nothing but 1 then. And then denominator would be less. And times 2 theta plus 1, then divided by 2 theta squared. Okay, so that means eventually the Fermat lower bound would be 2 theta squared n times 2 theta, then plus 1. Again, if you remember, I reminded you it's always n right here, not n squared, not n cubic, not square root of n, just n right here. Okay? Any question on this? Okay, it looks like I'm speaking to the air. Okay.
I have a question. Can I ask a question?
Yes, of course.
So on the right side of the screen and the third row, when you differentiate the difference of x1 and theta square over 2 theta.
You mean here? Hold on, you mean here?
Yeah, just about one line. Do you missing the 1 theta on the numerator?
No, so I read deriving this, right?
Yeah, I mean in the middle of the numerator, it shouldn't it be 2x1 theta?
2x1 theta, what do you mean? 2, 6, so are you saying this right here?
No, the numerator.
Here?
Yeah, in the middle of this numerator. Middle, the third item.
The third one?
Sorry, the second one. Sorry.
This one? Yeah, I wish you guys can have my board right here. Mm-hmm.
The line above it. I mean, the numerator. Yeah. I think it's x1 square minus 2x1 theta plus theta.
Oh yeah, you are right. Actually, yes. Thank you so much on that. No wonder I don't feel good about that.
Okay. Thanks.
Let me. Right. Okay. Thank you. So by any means, this answer is correct. Okay. If you do think about my derivation here is lousy, you guys can correct it. Okay. Based on me missing theta right here, I don't think it's correct. So you guys get deriving the right form of the second derivative of logarithmic function and to see if you can get the same answer as mine right here. Good. Okay. Let me clear out everything. So move to, okay, move to B. Let me see, B is, okay. Oh yeah, deriving MLE, I think you guys can handle it. Because you do see that we have score function and then second derivative, right? So I will let you to do it, but I do want to mention one thing. Again, like I said, I'm looking for trouble in these questions. It's not easy question, so let me directly jump to the log graphical function of the join PDF right here. Okay, you write your join PDF like in A. Then you basically end up this n divided by 2 theta square, and then you do have your 1 over n summation I from 1 to n, then xi squared. Okay, then minus theta plus theta. Okay, see if you can get it using square function. Okay, so then the goal is I'm trying to set as a 0, right? Set a 0 and trying to find what the theta head is. Okay, but as you can imagine, this guy is what? You do have quadratic function to solve. Okay, then how do you solve for quadratic function then, right? High school math, you guys figure that out. Okay, you have theta square, theta, you have something as theta square right here, right? So basically, only thing to solve is what? This function equals to 0. Okay, good. So you have theta square, theta, and you're solving for equal to 0. You know how to do. Okay. But it means that eventually there's one theta, which basically is 4t plus 1, and then square root minus 1 then. So t here is exactly is 1 over summation I from 1 to n xi squared. Okay. One thing I do want to mention that it's solving this equation, you do have 2 solutions, right? One is positive, one is negative. Then why we get rid of this then? Why we don't use this? The reason for that is theta is a variance bigger than 0, so you don't need a negative solution. Only thing positive, you keep it, the solution right here. Okay, good. Of course, need to deriving again. It's right here. I think it's not hard to derive in second derivative and show that it's what? Negative. Okay. Then the second derivative right here it's n theta squared. Then you have t right here, theta minus half. Okay. And you could show that somehow show this guy is positive actually. Okay, bigger than half, and this guy have minus 10 right here, so it's smaller than 0. Okay, good. So I'll let you to do it to say that it's basically theta head right here is your MLE. Okay, so if you cannot solve in this, let me know. Okay, we can talk on Wednesday on the office hour. Okay, again, we're going to using room to do office hour, unfortunately. Okay, so I think you guys can handle that in terms of mathematical estimation. Okay, then in C, then it's much easier to handle then. So right now it's you do have 2 estimators. One is x bar, the other one is x squared. Okay, and then I think what one can estimate theta using both. That means this guy by that normal theta and theta. Okay, you could use x bar to estimate theta. You could also using x squared to estimate the theta as well. Okay, I think the whole module of this learning is, okay, if you do have 2 estimators, then which one you're going to choose? We are going to choosing the smaller variance. That means we are deriving the variance of x bar and the variance of x squared. And then to compare which one have smaller variances. Okay, so then the first one I think is relatively easy. Variance bar and sigma square. Sigma square right now is theta. Okay, then variance of x squared. Okay, you should know how to do it right now because normality deriving variance x squared, we are always using what? n minus 1. Oh, what's wrong with my color? So then taking n minus 1, taking x squared divided by sigma squared, follow chi squared n minus 1. Okay, so right now, of course, we are having sigma squared as what? As theta right here. Okay, using that, you do know that the variance of whole term, theta n minus 1 x squared equals to what? Right? Variance of quantity right here, chi square 1, variance of chi square 1 is 2 times n minus 1 is a variance. Okay? By using that, that could give you variance of x squared. Okay? This whole thing taking out become n minus 1 square theta square, then equals to 2 times n minus 1 x. So that means variance of x squared equals to what? Move down to become 2, and then n minus 1, then theta squared x. Okay? So right now this guy is, let me see, make sure that, yep, I think so. Okay, 2 theta squared, then n minus 1. Okay, so then right here, let me take this out so I can talk about how you're going to compare between variance x bar and then variance of x squared. Okay. So right now you do have variance x bar is theta divided by n. You do have variance of x squared, then 2n minus 1, then theta squared. Again, how do we know this guy is bigger or this guy is bigger? Okay, how to do? Again, I told you in the class, it's just plug in, right? What if n is 2, right? If n is 2, variance x bar is theta divided by 2. Then variance of x squared is what? 2 theta squared. Okay? Then now you know that it's theta is bigger than 0. Could you see which one is bigger? Right? Theta 2 theta squared. Which one is bigger? I don't think you can have any uniquely bigger or uniformly bigger things. Theta divided by 2 or 2 theta is bigger. Okay? As you can imagine, is what? Theta. So if they are equal, theta equals to what? Okay, so if they are equal, I think theta equals to 1/4, right? Let me see. Oh, 1/2. Wait, 1/4, right? 1/4, right? So, okay, so let me see. 1/4, 1/8 times, yep, exactly, I think so. Okay. So that means it's not hard for you to draw that function to see what happens. So if equal theta is 1/4, that basically means that it's if theta smaller than 1/4, which one is bigger? Which one is smaller? Okay, I think if theta smaller than 1/4, theta smaller than, right? I think so. Okay, you could double check it. So that means That means if theta smaller than 1/4, then theta divided by 2, theta half smaller than, then told you that its variance of x bar is going to smaller than variance of x squared. You will prefer x bar. And then if theta bigger than 1/4, it'll be the other way around. That means variance of x bar is bigger than variance of x squared. Okay, so I'm told you that there's no uniformly beta estimation under this situation. It depending on what your theta value is to claim that uniquely variance, smaller variance estimation. Okay, sounds good in B or in C? Any questions right here in C? Okay, I don't hear anyone say no, so I'm move on then. Good. Yeah, so in D, again, it's oh, whoops, what did I do? Oh, I can actually using different whiteboards. So let's take this out. Oops, oops. Okay, so I think I can. Okay, so in D, the question like sounds confusing, but actually it's, say if I do have Tx right here, it's 1/n, then summation I from 1 to n, then xi squared. Okay, so can I find any tau theta? Actually, it's unbiased estimator using Tx. It's okay. So this guy nothing but really deriving what expectation of Tx. Okay. Then if you do that, just write that directly 1/n, then xi squared. Okay. Then this guy nothing but 1/n expectation xi squared. Okay. And then we do that. In the previous question, this guy would be eventually theta plus theta squared. And then whole thing out, n items, and then divided by n, then becomes theta plus theta squared. Okay, so it means Tx is an unbiased somebody sent message. Oh, you guys are chatting with me right now? Okay, I just figured that out. Oh, okay. So the condition will have a different theta, but I think moral of the story is no one is uniformly better. Yeah, I think so. To see it, what if n is not 2? You could put n bigger than 2, then you still think about, you compare the theta, right? Well, eventually you only need to talk about it. You're providing some evidence to say neither of them is uniformly beta estimation. That'll be okay. Okay, good. So, okay, then let me see if anything. So far, so good. Okay. Okay, good. Is that easier? Just like unmute yourself and talk to me? Maybe it's easier, I think. Okay, good. Okay, so is everyone okay moving up to D? Okay, I think so. Or you can keep chatting to me now. Right now, I do see where to find a chat. Will be fine. So, okay, so then going back to D, it's you do have expectation of Tx equals to, that means Tx is an unbiased estimator. Of T theta, of tau theta. Okay, good. So right now you find that tau theta is theta plus theta squared. And then you are trying to find CILB, okay? You're trying to find CILB for theta plus theta squared is, okay? Or you wanna say actually eventually you are trying to claim that it's whether or not variance of Tx is going to reach in CILB. We are trying to show this, okay? Show this. Okay, good. Let me see chat. It's much easier to send chats. That's embarrassing. Oh, okay. That's embarrassing. Okay, good. Okay, so then let's do it. Of course, we want deriving what CILB is. Okay. Right here, this guy actually easy to derive because you're working on something already in your previously, right? Expectation. U theta, then taking square, then right here. Okay, so one thing I want to mention is right now your denominator of CILB is still the same. So this denominator won't change because of tau theta. Making sense? So that means you do have that in A or B. Let me go back to A or B to see which one is what I'm looking for. I think in A, right? In A, eventually you're deriving your denominator. It's I think it's n times 2 theta plus 1, then divided by 2 theta squared. Okay, this guy from A. Okay, then only thing to do right here is what? You're deriving your tau theta. You derive your tau theta, d theta plus theta squared, then d theta. Don't forget about taking square, that is. So that means n 2 theta plus 1 divided by 2 theta squared. Then this guy is 1 plus 2 theta, then taking square then. Okay, you do see that this guy could cancel out one of that, theta to 1 plus 2 theta. And then eventually, I think 2 theta squared, then divided by n times 1 plus 2 theta. That's okay. Let me double check. Okay, so we can move on. 2 theta squared. No, so this is wrong right here, right? So this is wrong right here because I do cancel out 1 theta. It's not denominator, it's a numerator. Theta is. Okay, I think this is correct. And then the next one is much more tedious. You are trying to find what? What is the variance of Tx would be? That means it's a variance of 1 over n summation I from 1 to n, then xi squared. Okay? So, I really don't like to do this. This guy would be, if you do that straightforward, eventually you are going to find variance of xi squared. 1 over n squared, then because independence, I can write summation I from 1 to n variance xi squared. Okay? This guy would be really hard to find, and I could give you some easy way to do it. One easier to do it is because I do know xi follow normal theta then theta. Then I can actually do it xi minus theta, then square root of theta will follow the 101. Okay, so then my goal is, so let me think about it. So if I say this guy is zi, if I say zi, it's xi minus theta, then square root theta. Then I can basically show that it's xi equals to zi square root theta, then plus theta. Okay, good. So that means, let me see. Variance xi, yeah, I think so. So that means I'm trying to do variance of xi squared equals to what? I do have variance, hold on, do I miss anything? Variance xi, let me see. I feel like I missed something right here. Yes, okay. So that means, so that also means that xi squared is going to become what? Xi squared, this guy becomes square. That means this guy is zi squared theta, then plus 2 theta square root theta, then zi, then plus theta squared. Okay, you can see how annoying that is, right? So then that means this guy is zi squared theta, then plus 2 theta square root of theta, then zi, then plus theta squared. Okay, so I think I need to take something out. Maybe I can keep writing here. Maybe you guys still can see. So that means this guy is theta squared, then variance of zi squared. Okay. Then the second term would be what? The second term would be plus. Okay. So the second term would be this guy variance. So this guy is 4 theta cubic variance of zi. Okay. And then of course this guy don't have variance. Essentially you can take that out. So then that means you have covariance term right here. 2 plus covariance between what? This guy and that guy. Zi squared theta, then 2 theta. Oh, I run out of space. So let me take this out. First, I'll go back to this. Plus covariance. Covariance. I just write it here. Covariance. Okay. So I mean, in order to derive invariance at SI squared, you do need to derive in this guy and this guy and this guy. Okay, let's do that one by one then. So taking this out. Okay, so I think the covariance term is actually the most easy one to solve, I think. So covariance right here, to be specific, is zi squared theta. Then 2 theta square root of theta, then zi, right? In terms of covariance, you take every theta out. That means theta 2 theta square root of theta. Then covariance between zi squared, then zi. Okay, so right here would become something. Okay, I will just say the constant c right here. Okay, c right here. And then inside guy, if you're looking on the covariance, basically it's expectation, then zi cubical, then minus what? Zi squared expectation zi. That's what covariance is, right? Covariance AB, then expectation A times B, then expectation A, expectation B is. Okay, then I do need some space right here, pardon me on that. Okay, so we talk about ZI right here. ZI right here is normal 0, 1. Okay, then normal 0, 1, what does expectation ZI right here? 0, right? 0. Okay, so that means whole term is 0. How about this guy right here? Okay, normal 0, 1, symmetric. Okay, every R moment of normality is what? Actually, it's 0 then. Okay, R moment, ODD moment. Okay, it's 0. So that means covariance between ZI squared and ZI is 0. That means this guy is 0. 0 right here. Okay, then that diverts. Sorry about that. That diverts. That diverts. Oh, maybe I can create another whiteboard. Okay, that diverts working on the variance of ZI squared. Okay, good. So it's actually easy then. We do know about ZI normal 0, 1, right? ZI normal 0, 1. Then what does ZI square follows? Chi square 1. Okay? So that means ZI square, chi square 1, variance ZI, chi square 1. That means this guy is 2 then. Okay? And then because ZI normal 0, 1, then variance of ZI equals to 1. Okay? Because of normal 0, 1 of ZIX. Okay? So that means my final answer about variance of Xi is here, right? Again, it's, I think, identical, so eventually it's got 1 over n. Then variance Xi is here, variance Xi is here, variance Xi is here. So that would become theta squared. Then variance Zi is 2 right here. And then plus 4 theta cubic. Then variance of Xi is 1. Variance Xi is 1. Because Zi is 1. Sorry about that. And then covariance is 0. So eventually become this then. Okay, good. Let me double check that. Do I do it correctly? No, full theta. Yeah, I think so. Okay, good. So, okay, right here is actually looking at this. If working on it, sorry about that. Let me write it here. Right, 1 over n. You can actually take what? Take a 2 theta square out. You take 2 theta square out. Then eventually become 1 plus 2 theta. This guy exactly equals to CRLV we derived previously. Okay, so that means Tx, so 1 over n summation xi squared is an unbiased estimate of tau theta, which is theta squared plus theta. And then this guy also reaching their Cramer bound. So basically we can claim that it's Tx is an UMVUE of tau theta equals to theta plus theta squared. Okay, good. So any question on this?
Can I have a question?
Of course. Yeah.
So in the beginning, you said the denominator of CRLB comes from A.
Yes, exactly.
But A the A is not calculate the tx, it's just calculate the x.
No, so yes, no, so basically is this. So let me have another whiteboard right here. Okay, so we are looking for the CILB, right? Right here, it's for TX.
Yeah.
Right. So you're estimating, I mean, not TX, yes. We're estimating tau theta. We are looking for whether or not you do have a bias estimated for tau theta. And then the lower bound is what? Making sense? So that means right here it's, you are looking for CILV for tau theta, right?
Yeah.
Then right now CILV by definition it's d tau theta, then d theta, then taking square. Right here, expectation, you still writing down as right here. Because this guy is still using x1 to xn, follow normal theta theta to do inference. You start using x1 to xn to estimate tau theta. As long as the x1 to xn distribution doesn't changes, your lower bound, your denominator of CILB is always written down as expectation of a score function taking square. They'll be the same.
Okay.
Making sense? Okay. Your TX is a function of x1 to xn. It's right? Okay.
So do you mean that the score function stays the same? Okay.
Yes, exactly. Okay. Exactly. As long as you are doing x1 to xn, using x1 to xn to do inference on any function of theta right here.
Okay, thank you.
Okay, good. Anything else? Okay, good. So if not, we are going to talk about the second questions. Let me go to the second question would be number 5. It's okay. So let me take out a bunch of lists, trying to move on. Let's go on another whiteboard. Yeah, because I can go with unlimited whiteboards. Okay, good. So this one is 2006 master exam. So if you guys want to take a master exam, you do want to do a little bit of this. Okay. And then that's the reason why we have 6 hours from master exam, because again, the duration is not easy, but this is homework. You guys have a whole day at home, right? So then let's say that it's x1 to xn is random sample from normal mu 0 sigma square. Then pay attention to your mu or sigma square is known or unknown. So right now it's mu naught is a known number, so you don't have to estimate it. And then so that means you are trying your best to do estimation of sigma square. It's a known term. Okay, so right now it's what you estimate. I think it's not sigma square anymore. Okay, it say it's, I want to estimate in general is sigma as a gamma right here. Gamma could be 1, gamma could be 2, gamma could be 3, in general. Of course, if gamma is 2, you know what to estimate, right? If I want to estimate sigma square, you could possibly using simple variance to estimate sigma square. But right now, it's not straightforward if gamma is general. Okay, so let's do what if gamma is general then. Let me see, then derive the expression for what you consider to be excellent candidate. Okay, so then not only that, but also it's, I'm going to find, can I find U and VUE? Could I find U and VUE for sigma gamma? Then gamma is in general, sigma R is in general. Okay, so actually we have several steps right here. But again, it's, if you remember, I told at the end of the class before spring break is what? How do I find U and VUE? The most easy way to find it, get starting with, is find complete sufficient statistics to find U and VUE. If you check in the slides of the, I've got a unit, and then the last few slides, I talk about how to find U and VUE. I'll review it tomorrow in class, but you'll find out that it's the most easy way to find U and VUE is you find complete sufficient statistics first, and working on it, and then to find a bias estimator for gamma, for sigma R. Okay, so then the U and VUE things, the complete sufficient statistics, right here. Okay, this is normality. Then for sigma square, okay, or sigma gamma in general, right? It doesn't matter what gamma moment is. What is, ask yourself, what is your complete sufficient statistics for sigma squared, right? And then normality, exponential family. Then we learned that from class before spring break, or even emitter number 1 is, how do I find complete sufficient statistics for exponential family? Right, easy. You're just using the theory. That means if I can write it either in joint PDF, or I think in single PDF. If I can write single PDF, if I can write it as a C WXC theta. HX, if I can write HX C theta, then exponential W theta, then T XI. Okay? If I can write so, then eventually I can claim the complete sufficient statistics for theta is summation I from 1 to n, then T XI is. Okay? I think you should know that, how to find the complete sufficient statistic right here. Okay? So then, okay, just working on it then. So normal mu0 sigma square, I can write 1 over P join PDF 2 pi sigma square, right? Exponential minus 2 sigma square, then xi minus mu0, then taking square. Again, mu0 is a constant, is no quantity. So you just claim that what is hx, right? Of course, it's okay to write here. So xi from minus infinity to infinity, it's, I think. Okay, so that means you could have this guy. Oops, what happened? Okay, so what? Why? Okay. Okay, 2 pi. I can have 1 minus xi minus theta right here. This guy could become my hxi. Okay, then I could write down right here sigma right here. Okay, this guy could become my c theta, and then expectation. Then you just write down what? You write down it's minus 1 over 6 squared, then xi minus mu0, then taking square. Okay, then this guy could become my w theta. This guy could become my txi then. Okay, so that means I can use this txi as my tx, and then so I can right here, I can claim that it's summation I from 1 to n, then xi minus mu0, they're taking square, is a complete sufficient statistics. Making sense? Okay, So since you have the complete substitution statistics, then, sorry about that. If you remember how we talk about complete substitution statistics, right? Using that find U and VUE. So that means basically is, let me see, can I get whiteboard? Yeah, sounds good. And then I can go back to this. I don't have to take anything out then. Okay, so that means right here it's, so in general, if you can having that complete substitution statistics, say, hold on a little bit. So this theory called Lemon-Chapet theory. So say if you have Tx as a complete substitution statistics, and then if you also find out that it's unbiased for tau theta, then by Lemon-Chapet theory, you can claim that it's Tx is the U and VUE of tau theta. That's what Lemon-Chapet theory told you. Okay, I say in class it's, so this is perfect work. Okay, so normally how would we do it? We are trying to take expectation on the complete substitution statistics. Hopefully that's a function, is a linear function of your tau theta. It's a plus b tau theta, for example. The reason we want to show that is the reason we want to see that is we can actually easily do working on that to get an unbiased estimation for tau theta. Okay, so it means also by Lemon-Chapet told me that as long as this guy is a function of complete substitution statistics for tau theta, then I can claim that it's Tx minus A divided by B is the U and VUE for tau theta. Okay, so that means by any means it's you're working on some complete substitution statistics. Okay, take expectation, and then hopefully it's linear combination, linear function of your tau theta. So you can easily find an unbiased estimator of tau theta. Then it's a function of complete substitution statistics. So you can claim that one is U and VUE. Okay, hopefully that makes sense to you. So right here, we do have that complete substitution statistics, summation xi minus mu 0, then taking square. Is complete substitution statistics. And then actually, if I do so, divided by sigma square, this guy follows what? Okay. Luckily, you saw me do that before. This guy should follow chi square n. Okay. And then compared to the xi minus x bar divided by sigma square follows what? This guy follows chi square n minus 1. You don't need to know why one is followed chi square n. One guy follows chi square n minus 1. And I said this guy easy to derive because if you can write that xi minus theta minus mu 0 divided by, see, from here to here, I just put sigma inside the square edge. Okay, and you do know inside guy right here follow normal 0, 1 edge, right? Inside guy follow normal 0, 1, taking square follow chi square 1, then taking summation, then follow chi square n. Okay, easy to derive. And then let me take this out. Okay. So the reason for that is I can easily take expectation on summation xi minus 2 mu 0 square, then sigma square, right? This guy chi-square n, expectation of this guy right here equals to what? Equals to n. Okay, so it means I can also create it 1 over n summation I from 1 to n xi minus 2 mu 0 square equal to sigma square. Okay, that means this guy right here is unbiased for sigma square. Okay, as well as function of complete substitution statistics, because we say this guy is complete substitution statistics based on previous slides right here, right? We said summation xi minus mu 0 square sum is a complete substitution statistics. So this guy right here, not only unbiased, but also a function of complete substitution statistics. That means based on Levin-Shaffer theory, this guy xi minus 2 mu 0 square is the UMUE of sigma square. Making sense? The point is, right now it's okay. Say if gamma is 2, we could easily say so. We could easily say this guy right here is UMU or sigma square. But what if sigma gamma is actually gamma general and gamma from 1 to 2 to 3 to dot dot dot? What if gamma general? Okay. It's actually not that hard to find it, but hard to compute as well, though. So right here it's, I do know about, hold on a little bit. Let me go back to a little bit to previous one. Okay. I do know about this guy follow chi-square n. So that means in order to find something right here, unbiased estimator of gamma right here, right? That's what we are trying to find. Then you can actually easily to find it. It's, I do know about head right here. Okay. Then any questions? Hello? Okay. So say if I do say this guy right here, it's 1 over n summation I from 1 to n, then xi minus mu 0, then taking square. Okay. So that means I'm trying to working on one thing. It's so actually it's C right here. Okay. So like I said, it's if I can deriving right here. Okay. It may not necessarily equals to gamma square, gamma r exactly. But I cross my fingers saying it's okay, if I do that, could I actually find A plus B, then gamma, sigma gamma right here? So if I can derive in the left-hand side, and then it turns out equals to A plus B gamma R, then I can working on that to put it back as I saying is gamma head R minus A divided by B equals to gamma R. Then I find this guy right here. I find unbiased for gamma R. Then as well as this guy is a, oops. This guy is a function of, right here, right? This guy, inside guy is a function of the sigma head square. Agree? Okay, you can think about it. I can always write down this guy right here is square, then taking gamma out, right? Does inside guy look a function of sigma square is? Okay, it's a function of sigma square, okay, which is complete sufficient statistics, right? So that means what? That means by Lehmann-Schaffer theory, I can claim that it's sigma minus A divided by B gamma right here is the U and VUE. Okay? So that's our whole goal is trying to deriving this. Right? Derive this. Okay, to see what happens. Okay, so by derivation of that, let me work on this. Then eventually, if we go anywhere, we are going to reach the next board. Okay. Then, if you this is actually homework, I think maybe it's not, but I do remember I talked about it in class or maybe in previous years. Okay, so then how do you actually derive in this then? How do you actually derive in this? Okay, so if you would like to write this, you might see what I'm going to. So this guy right here, maybe it's not easy. So, but one thing would be easy is, so I may be missing n, but we can eventually get it back. Okay, so let's put another whiteboard, I think. So that means I'm working on this. I do know what this follows. I'm working on this. The reason I'm working on this is I do know inside guy follow chi-square n. Okay, then say if I name it as a y, how about I write it e, y, then gamma right here. Then yi follow chi-square n. Okay, then if that's the case, then how do I derive the expectation of y random variable but with power of gamma divided by 2? Then if y follows chi-square n, actually straightforward, right? You're just deriving from 0 to infinity. Then y with gamma divided by 2. Then times PDF of chi-square n. So chi-square n combination is gamma. Alpha, beta, alpha is gamma divided by n divided by 2, not gamma divided by 2. So n divided by 2, then with 2, right? Alpha, beta, I think so. Yeah, okay. So that means this guy is alpha, then beta alpha 1, then x alpha minus 1 expectation minus, then it's actually y, no, y. So minus y divided by beta, then dy. Okay, good. Well, even though I say it's hard to derive, actually not out of principle, because I can actually take this guy out and divided by 2. Then I can, from this infinity, I do have y right now become n divided by 2 plus gamma divided by 2 minus 1 expectation minus y divided by 2, then dy. The reason I want to write so is what? Is I actually want to create a new gamma distribution. This is my alpha, then this is my new alpha. Okay, then this is still my beta right here. Beta doesn't change, but I do need to have the beta with gamma n divided by 2 plus divided by 2 right here. Okay, I'm trying to create a new alpha, then still the same beta right here. Okay, such that I will know that whole thing will be still PDF. Then such that the whole thing will become what? Will equals to 1. But the point is, I do creating extra term right here. So I need to compensate it. Then I'll write compensation right here, okay? I do need some compensations, gamma n divided by 2 plus gamma divided by 2. Then 2n plus 2, then plus gamma divided by 2 to compensate it. So that means eventually right here equals to what? I will do as much as possible, but I don't know if how much far I can go. I think only thing I can go is this. Possibly. Then we double check it. Yeah, I think so. Perfect. Good. So that means, of course, this guy right here, Okay, good. So that means I'm deriving this right here. Okay, good. So that means in the right here, in the left-hand side right here, I can do what? Eventually it's expectation of sigma gamma if you put down your right here, right? And then you have your summation xi minus mu 0 square, then with that as power divided by 2 right here. Okay, so that means this expectation equals left-hand side as a constant, say constant right here, let's say C right here. So that also means that it's what? That also means that it's, I can write expectation of C inside, then summation xi minus mu 0 square, then taking as a gamma right here equal to sigma gamma. Okay, good. So this is exactly what we are looking for, right? I do have, sorry, it's really ugly right now. So let me take that out. Equals. Okay. Why do I want looking for that is what? This guy right here is unbiased of sigma gamma. Okay. As well as what? Function of complete sufficient statistic, right? This guy is a complete sufficient statistics. Okay. So again, it's what? By Lemon-Chaffee. I do know this guy right here, this guy right here, this guy right here, it's the UMVUE. Making sense? Okay, I do know this guy looks a little bit ugly, so you want to do one thing to trying to get that it's more beautiful. I think which is what? Which is, let me see if I can give you a better form of the final estimation. It's okay. I think eventually that guy, if you say TX right here, hold on, let me see if I can give you a beautiful form of the. No, I don't think that beautiful form right here. So anything, only you can do is trying to simplify right here. Okay, trying to do this guy right here. Well, by any means is, you know what I'm saying, and then even this form is ugly, you can still write it on your paper to show that it's a UMVUE. Okay, good. So any question on this? Okay, if not, I think if we can have everything for today now, it's 1:34 already. Okay, so if you have any questions, let me know. So I'm going to leave the meetings. So I will see you guys tomorrow then. Bye-bye.